we go with our next presentation. Today's subject is work, power, and energy. As always, I would encourage you to take the information that's given to you and think about all the different places that you can imagine where that topic could be taken. Now, certainly when you talk about power and energy, you can talk about in the modern society that we have, how we utilize power and energy in so many different ways. And then what are the connections between our energy use and other things in society? There's so many questions and places you could take this thought process of work, power, and energy. But today what we're going to do is just take the basic physics of work, power, and energy. And from a basic physics standpoint of view, work is the force multiplied by the distance. So that's the idea of work, just force multiplied by distance. You have to have some kind of motion for there to be work being done. And of course, if there's motion, we're back to talking about kinematics, so we're going to tie all of this stuff in together. So just a force isn't work in itself. If you're pushing up against a rock all day long, if you don't move the rock, you're not doing any work on the rock. Okay, so here in a simple diagram we can talk about the idea of a force being applied, and then the delta x here would be the displacement along the x-axis, displacement in the x direction. So there you can see that the force and the displacement are parallel to each other. But that's not always going to be the case. So here we have a force that's being applied at an angle, and we should understand that it is the component of the force in the horizontal direction that is parallel to the displacement. So really it's this parallel force that is doing the work. This force over here will go into other things, as you can imagine, like normal forces. Now let's see. That means that the formula for your physics AP formula sheet is going to be like this. Work is the force parallel to the displacement, meaning the force multiplied by the displacement multiplied by the cosine of the angle between them. Now in a case like this, the angle between the force and the displacement is 0. So if the angle between them is 0, cosine of 0 is 1, this formula works whether you're at an angle or whether you're not at an angle. Okay, so something to remember, of course, we know is that an object has a weight to it, and if you're going to lift it, the force is going to be the weight of the object. So here's a person lifting a car in their house. I don't recommend this, but looks like that piano is in some jeopardy there. But there we go, and we remember that the weight is the mass multiplied by the local acceleration due to gravity. So we can use this if we're lifting a car in a living room anywhere in the universe. Okay, so here's a problem for you using an angle. See if you can solve this one, and when we come back we'll talk about the answer. Okay, here we go again, and there's a diagram to help you picture that. A couple people pulling sleds across the snow. Alright, well, what do? It's the force multiplied by the displacement multiplied by the cosine of the angle between them, and I got this number. So if you didn't, we can talk about it in class, of course. Okay, now the J after the answer is the joule. Work is measured in joules, so the amount of work you do is the amount of joules involved. So that's just the unit. It's a derived unit out of newtons and meters because work is force multiplied by distance. Newtons multiplied by meters become a derived unit called the joule. Okay. All right, so power is how fast you can do the work. So how fast are you doing the work, basically? We could say that power is the work divided by the time. So we'll start with that as our formula, and we'll refine it to be more in line with the AP formula sheets a little bit later. Okay, so try this one. See how you can do. When you come back, we'll discuss the solution. All right, are you back? There's a guy lifting some weights. And there's another person doing that. And this is the work I got. The work divided by the time gave me the power. Hopefully that worked out for you. Okay, let's see. Try this one too, seeing with power, and see if you can tie in the two concepts now. And we'll talk more when you're back. Okay, here's the answer that I got. And you can see I didn't do a great job on the significant figures there. But hopefully you got something similar to that. And also we can talk about the W now. The W is the symbol for power, and the symbol for power is the watt, W-A-T-T. You've probably heard watts already, maybe with light bulbs, but watts and kilowatt hours are very important in talking about electric bills and all kinds of fun things that you can look forward to when you are out there in the world paying these bills. But we all are too, and these are considerations that we should be talking about. Okay, connections that we can make to our class material. Okay, so now we're going to talk about mechanical energy. Energy is the ability to do work. So, okay, if we're talking about the idea of doing work, then it's going to take energy to do it, and that seems like a natural thing for us to understand. So the unit for energy is also the joule. If you're going to do 1,000 joules worth of work, you're going to need 1,000 joules worth of energy to make that happen. Work and energy are related, and we'll tie them in a bunch before this presentation is over. Okay, so we could talk about energy of motion. That is called kinetic energy, kinetic for motion. And the formula for that is 1/2 mv squared. The symbol is K. This is consistent with your AP formula sheet. K is equal to 1/2 mv squared. Okay, so how about this one? Just a quick problem for you. Give it a try. Come back, of course. Here's the answer I got. Again, not so great with the significant figures, but there we go. Okay, and then we could talk about stored energy. On your AP formula sheet, the letter U is used for stored energy. So that's potential energy, energy that could do some work. The gasoline in your vehicle is a good example of that. It's got the potential to do some work. All right, so let's see here. But one type of potential energy, okay, where you're at, you can do some work just by falling. You know, you've got a weight to yourself, and if you fall a certain amount of distance, you could do some work on the way back down again. So potential energy because of gravity is one that we're going to be talking about. Now on your physics formula sheet, your AP formula sheet, they'll say that the change in your potential energy due to gravity is your weight, that should make some sense here, multiplied by how high off the ground you are, your displacement in the y direction, or actually your change in position, because this is talking about change in potential energy. As you do work on something and lifting it, you are giving it a positive potential energy. You're building up its gravitational potential energy. And as you drop it and as it falls, gravity's doing work on it and it is losing its potential energy. So the object as it changes its height in the negative direction is going to be losing potential energy. So that's because of its position. Okay, so gravitational potential energy. So there you go. What's the gravitational potential energy of this object? And there's the answer that I got. Give it a shot and see if we're in sync there. Okay, so here's a basic principle of physics here. Energy cannot be created or destroyed, only transferred from one form to another. Conservation of energy. Well, that's interesting to be talking about, and it's very important there that they've got the idea that the amount of energy in the universe is standard. There's no change in the amount of energy in the universe. It goes from one form to another. That's a pretty crazy concept to be thinking about. We're talking about you can't lose the energy, you can only go from one form to another. And I get that when I talk about the idea of this napkin. This napkin has potential energy, and as it's falling, it has less potential energy but more kinetic energy. That seems to make sense. But how about when the napkin hits the ground or the table? Now it has no kinetic energy and no potential energy. How did I destroy that energy? I'm breaking the laws of physics, I don't know. But that's something I'd like you to think about and we can talk about in class. Okay, so if mechanical energy is both kinetic and potential energy, we could say that if we're conserving the energy, that there's no change in mechanical energy. And this is a safe one that I can make. I can't poke too many holes in this one here. But this means that for every bit of potential energy that you lose, that's your gain in kinetic energy. The triangle is the delta, a change in symbol. So the opposite of the change in potential energy is the change in kinetic energy. All right, so this idea of gravity here is a conservative force. So if you're talking about the work that gravity does in converting potential and kinetic energy back and forth between themselves, you're going to say that energy is conserved. So if the forces involved are conservative forces, and as I say, gravity is a conservative force. In a conservative force, the work done is independent of the path taken. Think about that on an incline. How much work would it take to drop an object? How much work would gravity do, I should say? How much work would gravity do if I dropped an object from 1 meter, or if I put it on an incline 1 meters high and then had it on an angle of 30 degrees, let's say, or any degrees really? So what would be the difference in the amount of work there? That's something to think about. But then 30 degrees makes it an easier calculation. How much work would gravity do there? Try that one. We can talk about that in class also. But I think you're going to find that the work there done by gravity doesn't matter whether you drop it or whether you put it on an incline. So something to look at. Okay, so conservative forces are the kind of forces that will have potential energy. Can you think of any other forces that have potential energy? All right, let's see. All right, so this is a standard problem that we've been doing for a while. We could find V final here pretty easily, I think. So try that, please, using the kinematics that we've used, the formulas that you've used so far, and then try using it with the formula there saying that the negative of the change in potential energy is worth the change in kinetic energy. And I think you're going to find the same answer. But give that a try. That's a good one to convince yourself that these things are related. Either way, you should get 14 meters per second, so give that a try. Okay, so it should make some sense here then from what we've talked about before, that if an object is moving, if it has a speed, and you want to change its speed, well, that's an acceleration. And an acceleration is going to require a force, which means work will have to be done. So if you are causing an acceleration, with our new language here, we could say we're also causing a change in kinetic energy. So it should make some sense here that work and kinetic energy are related to each other in that way. So here is the work energy theorem. The sum of the work done on an object is equal to its change in kinetic energy. As a challenge in class, we'll try to solve that one. See who can come up with a solution to that one. We'll talk about that one in class. Who's able to show that, given the concepts that we've already developed, that this new thing is true? That's pretty clever. Okay, so here's a problem to get you started. This is pretty straightforward. How much work would have been done on the object? So think about that one. And that was the answer that I came up with. And if this was the distance, what would the force be? So this is a way of applying that work energy theorem. Again, not too good with the scientific notations, am I here? The amount of significant figures, rather. But let's see here. And then my question is another one for you here. So hopefully those worked out for you. How about this one? And again, how much work was done by friction? And if that was the distance, what was the force? And how about adding in the coefficient of friction? So here we get the idea of the negative values as well. So those are pretty quick and straightforward, and here's the answers that I got for that question. Here's a tougher one for you to try, so of course you can be pausing as you go. And I would recommend on this that you try a problem like this to convince yourself and to sharpen your skills. Try it using what I had presented before this presentation, using kinematics and Newton's laws, and then try to do it with the energy considerations. And either way, depending on rounding, you should get an answer right around 0.461 meters. Okay, a couple of these formulas are expanded on and presented in a different way on the AP Physics formula sheet. And I'm sorry, a little ahead of myself there. So a conservative force, I've talked about conservative forces, and friction is not a conservative force. Friction is going to be dependent on the path taken. If I use the friction on a table going straight across the table, that's a lot different than having a zigzagging path where friction would be doing more work on it. So friction is not a conservative force, and remember, they can now change the mechanical energy. Conservative forces don't do that. Okay, so remember again also, non-conservative forces cannot have potential energy, but they can change the mechanical energy. So here I'm giving you a little something to go on, and that is that the work of the non-conservative forces is equal to the change in mechanical energy. And that's another pretty powerful relationship to solve some of these problems. Okay, as I was starting to mention before, your AP formula sheet presents these things in a little bit of a different way. Since work and energy are related, they give you this relationship. We can talk more about that in class. And here, power being the work over the change in time, the rate at which work is being done. They're tying in the energy concepts there as well. But we can talk more about that in class, and I hope this presentation was helpful, and look forward to seeing you back there in the classroom. Ooh, look at that.